Hey everyone, welcome back to our discussion of matrices. Today we'll talk about the inverse matrix. Now, before we start our discussion, there are a few things we have to know about inverse matrices. First of all, if a matrix is not square, then it cannot have an inverse matrix. So let me write that here. Only square matrices can have inverses. Now, don't take this to mean that all square matrices have inverses, but if a matrix has an inverse, then it must be a square matrix. In other words, if a matrix is not square, then it has no hope of being invertible. Now, what do we mean by an inverse? Well, remember that we said that matrices act. Then the inverse of a matrix would somehow have to undo that action of the matrix. We've already seen this matrix in previous videos. Let's do one step of elimination. So I'm going to take the first pivot and eliminate only the 4 underneath it. So the operation that does that would be, let me rewrite it again here. 2, 4, negative 2, 4, 9, negative 3, negative 2, negative 3, 7. The action that we want would be R2 minus 2R1 into R2. And what we're going to get will be 2, 4, negative 2. Now here we get 0, 1, 1. And the third row is the same. So this is just one step of elimination. We usually combine 2 steps to remove or eliminate all numbers under a pivot, but for this purpose, this is enough. Now, last time we talked about elimination matrices, and we discussed how we can find the matrix that corresponds to this operation. And we did that by applying the operation to the identity matrix. So let me do that. I start with the identity matrix. It has 1s along the diagonal and 0s everywhere else. I'm just not going to write the zeros. All the empty spaces are zeros. And I'm going to apply this operation R2 minus 2R1 into R2. And what I will get is the matrix of elimination E. So the first row stays the same. The last row also stays the same. And then in the second row, I have R2 minus 2R1 column by column. So in the first column, I have 0 minus 2 times 1. That gives me a negative 2 here. Then I have 1 minus 2 times 0. That's just 1. And then I have 0 minus 2 times 0, which is 0, so nothing in that third column, and the third row stays the same. So this matrix is that matrix of elimination E. What this means is that the old matrix, so how can I apply this operation over here as or how can I represent this operation as matrix multiplication with this matrix E? Well, I can simply write 1, negative 2, 1, 1, with all the rest zeros, times the matrix A, 2, 4, negative 2, 4, 9, negative 3, negative 2, negative 3, 7, equals the matrix obtained after one step of elimination. So 2, 4, negative 2, 0, 1, 1, negative 2, negative 3, 7. So we have this equation with matrix multiplication, something very precise. We have equality. I have A and E labeled. Let me call this new matrix A prime, for example. So what we have is we applied E to A on the left-hand side, and we got A prime. It's very important that E multiplies A on the left, because otherwise an action on A on the right-hand side acts on the columns. We didn't discuss this last time, but, and I'm not going to go into any depth in here, but it's important to know that if we want a matrix to represent row operations or to act on the rows of A, then we have to apply it on the left-hand side. So we have this operation. And now let's focus not on the matrix A so much, but rather on the matrix E. So E acted on A, acted on A to produce A prime. Now the question is, how can I undo E to go back? So let me ask that question. How can I undo the action of E to go back to A? The question is, can we undo the action? Well, in this particular example, because the action is an elementary row operation, we can go back. So what action would reverse the operation R2 minus 2R1 into R2? So what did we do here? We took away 2R1 from R2. But note that R1 in A and R1 in A prime have not changed. They're the same rows. So I can go back. If I were to reverse subtraction by addition, I would go back. So the inverse of this operation R2 minus 2R1 into R2 is R2 plus 2R1 into R2. Now, if E is 1, negative 2, that and these ones along the diagonal, then E inverse, that's written like this, E inverse, would be the matrix that represents the second operation with the plus. And you see the only difference is whether we have a minus 2 or a plus 2. So inverses of elementary row operations are actually rather easy as long as they represent exactly one elimination step and not two elimination steps, because their things may be different. Not necessarily, but they can be different. So if we now apply E inverse to A prime, we're going to go back to A. Let's see that that really happens. So my claim is that E inverse times A prime equals A. Let's make sure that that's really so. So I have this operation 1, 2, 1, 1 applied onto A prime, which is 2, 4, negative 2 in the first row, then 0, 1, 1, and negative 2, negative 3, 7. Now I can carry out this multiplication as multiplication of matrices, or I can simply remember that this matrix represents the operation R2 plus 2R1 into R2. So I can just apply that operation on the matrix A prime, and that's exactly what I'll do just because it's easier. And immediately I see that the first and the third rows need to stay the same. So really I just have to focus on computing that second row. So I have 2, 4, negative 2. And then second row is 0 plus 2 times the first row. So that's a 4. Then 1 plus 2 times 4. That's a 5. Why do I feel like... That's okay. No, sorry. 1 plus 8 is 9. Yes, I did have a mistake there. So that's a 9. Then I have 1 minus 4. This will be negative 3. And then I just copy the last row because I didn't act on it. So this really is a this works. We have inversed the action of E by acting on E inverse. Now, for elementary row operations, we can find the inverse by simply looking at inverting the action. So subtraction becomes addition, addition becomes subtraction. If we multiply by a number, C for example, then we can reverse the action by multiplying by C inverse. So if you have E that equals something like this, say we multiply the first row by C, then E inverse would be 1 over C, 1, 1. In fact, we have this case for diagonal matrices. If you have a diagonal matrix, so diagonal matrix is a matrix that has all of its non-zero elements along the diagonal. Let's say it has these components A, B, and C, and none of them are 0. Then the inverse is just going to consist of the reciprocals, 1 over A, 1 over B, 1 over C. Now, just note that A, B, and C don't have to be whole numbers. They could be like a third or a fifth or a seventh, and then the reciprocal would be 3, 5, 7, and so on. Now, when it comes to permutations, if the permutation made a single exchange, then the permutation will be its own inverse. So if we have P equal to, for example, exchanging the first two rows would look like this. The second row would be in the first row, and then the first row of the identity matrix would be in the second, and then the third row will stay unchanged. So what is the operation described by P? Well, that's simply R1 and R2 are changing place. Well, how do you go back from such an exchange? Well, just repeat it, right? So we see here that in fact, P is also P inverse. If we apply P twice, then we go back to our original matrix A.